Hello, everybody. Let us start our discussion today. Today, we'll talk about a very special radiation which is usually known as the 21 centimeter radiation. Before we dig into that, let us look at what we have learned about the emission and absorption for a two level atomic system. Specific intensity of such a system, emission happening only from such a system, let me write it this way. This we calculated last time, which is given by h nu naught by 4 pi. Nu naught is the frequency at which the emission is happening. Remember, n is what we called the column density. So let me just put n over here, which is integral over ds on the number density. And this assumes that phi is independent of s, but that's all right. For the time being, we'll carry on that assumption. We also calculated how the absorption coefficient looks like. The absorption coefficient for such absorption can be written this way. N is the number density and phi nu. Okay, these are the things that we had got last time. And we'll carry forward from there. And let me mention what is the transition that we talk about. One type of transition we know of is one electron in the ground state of atom n equals to 1 level going to n equals to 2 level, or 2 level to 1 level. That gives you Lyman alpha transition, say. But these transitions are called electronic transitions because it's the electron that goes from one level to the other level. Here, we are looking at a transition of an atom The atom is hydrogen atom. The ground state hydrogen atom is often denoted by H and then the suffix Roman 1. So what we have in this, remember that it's in the ground state, so the electron is in the lowest level, and there is a proton. Let me draw that with P here, and it has an electron, right? The electron is in the s orbital. Now, both of these electrons and protons, they have spin. They're spin half objects, right? Electrons and protons have spin, and magnetic moment corresponds to that. And spin magnetic moment. So what may happen is the proton spin magnetic moment can be seen by the electron or vice versa, and there can be an interaction between that spin magnetic moment of proton with the electron. Now in such case, I can consider these states. States means the configurations of the system. In one case, say both the spins are aligned. So I'm drawing an up arrow. It can be a down arrow also. Basically what I'm saying is that both of their spins have the same direction. So this has half spin, this will also have half spin. And you know that the total spin of the system will be, so here I am writing the spin of the electron, here I am writing the spin of the proton, here I am writing the spin of the atom, because now I am adding this two up and they are in half projection, so here the spin of the atom becomes 1. On the other hand, I can also consider a case, so let me make this a little bit colorful for you. So these are when I am talking about the spin and talking about different states here. Now in this case, I can also calculate what is the value of G. G is the multiplicity of the state. Multiplicity of the state. Now because S is 1, G is 2S plus 1, so the multiplicity of this state is 3. And the other example I can have, the other way they can arrange is that their spins are not aligned. So there can be only these two. So which one is up, which one is down, depends on your definition and up and down. So that really doesn't matter. What matters is that if one is half, the other is minus half, and the total spin is 0. So with my convention, I can write G downstairs here. So G can be written here. What will be the multiplicity? Well, 2 into 0 plus 1 is 1. So the multiplicity G is, in this case, is 1. This splitting of the line, so what is happening is the ground state is split into two. One has certain energy and the other has a little bit of different energy. One has multiplicity 3, the other has multiplicity 1. This splitting is called hyperfine splitting. And as you can imagine, this gives us a two-level system, and there can be transition between these two levels. So I can get an energy or frequency. Energy between these two states gives you the frequency. And if I call that nu 0, now this is 1420 megahertz. But as I will write, you will realize that this must be a very, very important transition line, such that people have cared to calculate the frequency of the line to this much accuracy. It's known up to millihertz accuracy. So 1.4 gigahertz known up to millihertz accuracy. So you can imagine how important this line should be, such that one knows it up to this much accuracy. And the corresponding wavelength comes out to be 21 centimeter. I'm not writing all the decimal places now. And that's why this radiation is called a 21 centimeter radiation. And it's of enormous importance in astrophysics and cosmology. Enormous importance. One cannot emphasize the importance of this line anymore. Now looking at this frequency, it's coming in 1420 megahertz or 1.42 gigahertz. This is a radio frequency emission. 21 centimeter is a radio wavelength. So you use radio telescopes to see this essentially. Why is this important? The reason is simple. Most of the universe in most of the time is hydrogen. 2/3 of the universe is hydrogen. So if I able to probe this line, I should be able to know how much hydrogen is there. And that's it. That's why it is important how much neutral hydrogen is there. I will be able to know because this is coming from hydrogen atom in ground state. It's a neutral hydrogen atom in ground state. It must have that electron. Otherwise, there is no question of asking what is the spin difference between these two states, these two objects. So this probes the neutral hydrogen, which is everywhere. It's everywhere in our galaxy as well as in the universe. So it gives you many information about our galaxy and the universe. Let me also write down the A of this line, the Einstein A coefficient. It turns out to be enormously small. If you remember, the value of A for Lyman alpha was about 10 to the 8 second, 10 to the 8 per second. So for Lyman alpha, if you have one atom, it can go transition, Lyman alpha transition 10 to the 8 times a second. For this, for one atom, it takes 1 by 2.85 into 10 to the 15 second, which is about 10 to the 7 years. So in 10 to the 7 years, if you keep one atom, it may go this transition. So this transition is extremely rare. In terms of spectroscopy, such A values comes in highly forbidden transitions. Not only forbidden, highly forbidden. Yet, as we have said already, that for astronomy and cosmology, this is the transition one looks upon. Why is that reason? Okay. So what A tells you, if there is one atom in the upper state, then what is the probability that it will come back to the ground state? So with the numbers that we have written down for this particular transition, let us first ask the question, what is the probability that an atom will be in the upper state compared to the ground state? So let's first try to do that for, so the example that I take first, example, some optical transition, not a radio transition, some optical line, and say the frequency is nu naught is 10 to the 14 hertz, so that is in the optical range. So remember that ratio of the atoms in upper level to the lower level. This is, we wrote down this, this comes from the Boltzmann's factors, is Gu by Gl e to the minus h nu by kBt. Okay, so remember T is the temperature, so this nu is nu naught essentially. So let us have an estimate of what is Nu by Nl for such an optical line. And the ratio of Gu by Gl, just for the sake of understanding, let us take it to be 1. It can be, like for example, in the 21 centimeter line, this is the upper, this turns out to be the upper level, this turns out to be the lower level. You can see that Gu by Gl is 3. But there is no harm, so we will see that the conclusion that will come up to does not change if it is instead of 1, it is also 100 or 1 by 10. The typical temperature one deals with in astrophysics, systems vary, but let us take a temperature of say 100 Kelvin, just a ballpark number that we will use to understand this. So I have this quantity in the exponential. So if you calculate for this frequency 10 to the 14 hertz and temperature of 100 Kelvin, this will come out to be of the order of 50, which implies Nu by Nl is almost 0. It's much less than 1, much less than 1. So which essentially we always say that there is always lesser atom in the upper energy state compared to the ground state. So that is what is, if you just leave them in thermal equilibrium, this is always the case. Okay, so this is one example that we talked about. So let's talk about another example, which is the example of the H1 line. In this case, nu naught is, so let's not be so much particular, but it is 1.42 into 10 to the 19 hertz. Sorry, 10 to the 9 hertz, not 19. So H nu naught by kb T, what we have done is that 14 has become 9. So there is an order of 5 difference, 10 to the 5 difference. H nu naught by kbt, if you calculate, this will come out to be 0.679 into 10 to the minus 3. It's a very small number, which will give you Nu by Nl equals Gu by Gl times e to the very small number. How much is e to the very small number? E to the 0 is 1, so it is essentially this. And we have already seen that this quantity is 3. So this tells you there is, in this particular radiation, there is 3 times more atoms staying in the upper state compared to the lower state in thermal equilibrium. There are so this is neutral atomic hydrogen. So let's write that. What is that we call, you call this H1, right? So for now on we'll write H1 only. In the upper level, in the upper energy level, than lower. That's a plus point because you see the probability of transition is already less, but this gives us some hope because we have been at least managed to keep more in the upper level than the lower level. So once we know this, let us try to calculate the 21 centimeter emission. So I write this as I H1 is a function of nu. It's a function of frequency, right? So let me write that function of frequency like this. I was writing it in suffix so far, but because I am writing H1 in suffix now, so the nu comes there, and this is for emission. So let's see what it should be. We have the formula for it. So H nu naught by 4 pi AUL, whatever the value is, I have 1 plus GL by GU, and then this quantity over here for 21 centimeter just calculate to be 1. GL by GU is 1 by 3. So this quantity is 1 plus 1 by 3. So let's see what I get. I get H nu naught by 4 pi AUL 1 plus 1 by 3 phi nu, and then the column density of H1. The denominator is essentially 4 by 3. So that gives me a formula for the 21 centimeter radiation emission. And this is something very important. And remember that the IH1 is a function of direction in the sky. So I can write this as like n cap. N cap is the direction in the sky. 3h nu naught by 16 pi A21. Okay, so we are writing AUL. So let me write AUL here. Sometimes it's also called 2-1 because just it's two hyperfine levels. It's going from the second level to the lower level. So that's why. We have assumed so far that phi nu is independent of the direction along which we have integrated. What depend on theta is then essentially this. The column density can be different as you look at different direction. So not theta but n cap. N cap is the direction. So in different direction we can have different column density. And then of course phi nu. Okay. And for this emission in radio frequencies, so let's also keep that information here. Emission in radio frequency so this should not be there, but anyway, let us keep the information here. Emission in radio frequency, natural broadening is negligible. Okay, so all that broadening, the line shape function gives you broadening of only, okay, so there can be other things, but mostly the thermal part. So this mostly thermal broadening. There can be other thing, and that other thing is what I work on, but I am very much tentative to tell you that, but I will not. I just assume that it's only thermal broadening. Now, if I look at this expression, what I have up to here are all coming from the atomic processes. So they are independent of the cloud. The information of the cloud, there are two. How much is the column density and how much is the temperature? So information of the cloud in IH1, actually there is more, is, at least let us count. One is the column density. It's directly proportional to the column density. Second is temperature. There is one more thing. Let me draw the line, the intensity now, not the line shape function, the intensity as a function of frequency. If I draw this, what will I see? So let me use this color. So I will see that there is this Gaussian profile. There can be several of them, but let's say one Gaussian profile. The height of this profile tells you about NH1, because if NH1 is more, this height will be more. The width of this profile, as we have seen in the last class, tells me about the temperature. So you get the temperature, you get the column density from the same spectral line. There is one thing more. Remember that I have this cloud and I am on the earth as an observer. This cloud is emitting in H1 in 21 centimeter. This is a H1 cloud and I am looking at it. But this entire cloud can have a velocity which is, it's maybe going in some direction. So it always, everything in the world has some velocity. So this may have some velocity. So the line of sight component, the line of sight is the line which joins the observer and the center of the cloud. The line of sight component of that velocity will give you a Doppler shift in the spectral line. So this maxima will not be at nu zero. It will be at a Doppler shifted frequency. Looking at that shift, I can figure out what is the line of sight velocity or line of sight component of the velocity. Of the cloud. So that is the third thing. Which is velocity. So single observation of a spectral line in emission gives me all these three information. It gives me about the dynamics, thermodynamics, which is temperature, and the density or the column density. Not the density, but rather the column density. It's quite interesting, right? This has a lot of applications. Let me tell you about one of them. We look at external galaxies. We look them at in 21 centimeter radiation. Now, these galaxies are, we're mostly says talking about spiral galaxies. We will learn about galaxies in a lot more detail. They are like disk. It's circular, but the disk usually is oriented with respect to you because it's a two-dimensional object, and from an angle it may look like an elliptical. So this is the observer say. You turn your telescope towards the disk, towards the galaxy. Now this galaxy may be having a velocity in this direction. Okay, so let's call this Vg. And it has a component along the line of sight. So I will be able to measure that line of sight component of the galactic velocity. Line of sight, let us write LOS. Okay. I can figure out how much H1 is there. So this is the 0th point. It's not as interesting actually. How much H1 at different radius. Let's call this Rg. Rg is nothing but radius from the center of the galaxy. So how much H1 is there if I assume that it's like isotropic? So how much is there at a different Rg? You can actually figure out the entire distribution. You can ask the question, do you have spiral arms in the atomic hydrogen? Are they distributed with spiral arms, etc.? But this is one thing also you can ask. Now it turns out that this disk is rotating. Okay, let's see what happens if I look at a rotating disk. And this is quite interesting. So say this is my disk. I'm looking from here. So this is the observer. And this disk is rotating like this. See, the H1 at this edge is always coming towards you. And the H1 here is always going away from you. Which means here I will see that the H1 emission is, the frequency will increase, so this is blue shifted. Here H1 emission is red shifted. In fact, at different position in the galaxy, the velocity of the H1 will be different. And because of that, as we have seen, that this peak appears at the Doppler shifted frequency, the peak will happen at different frequencies at different parts of the galaxy. So what I will be able to measure is the velocity of H1 or velocity of the rotation of the disk. This gives you a lot of information, and one of the conclusion that comes out of the measurements of this velocity of the H1 disk of a galaxy is the fact that these galaxies host a huge amount of dark matter. That we will discuss later, but for the time being, this is what a single example H1 observation can do. Okay, so let us move on and let us ask the question, is it only emission? But if this line is also useful for absorption. There is a lot one can talk about in H1 emission and absorption and its use, but we will spend only this lecture to do all the talking, and because of that, obviously, our discussion will be limited. So alpha nu, if you remember, was given by c square by 18 pi, 8 pi, sorry, AUL by nu square 1 minus e to the minus h nu by kt, nu naught, not writing b today at least for Boltzmann, 1 plus gl by gu e to the h nu naught by kt, small n number density, and then phi. And for it, so this was in general. So let's see what are the changes for h1. For h1, gl by gu is 1 by 3 e to the h nu naught by kt. This we approximated to 1, but this is, to be more precise, it is 1 minus h nu naught by kt. So it really doesn't matter when I am comparing it, multiplying it with 1 by 3 and then adding it up to 1, this extra term doesn't matter. But when I calculate 1 minus e to the minus h nu naught by kt, then 1 will cancel out. So this 1 minus e to the minus h nu naught by kt is essentially h nu naught by kt. And if I plug in all this, so now alpha h1, it's a function of nu as always. This will come out to be 3. Where is this 3 coming from? Well, I have 1 plus 1 by 3, so it becomes 4 by 3 again. That 3 goes upstairs, and that 4 makes this 8 to 32. So 3 by 32 pi h c square AUL by nu 0. So I'll get one nu 0 here, and there are two nu 0 downstairs, so one of them survives. Apart from that, I have n by t phi nu. See, for the emission formula, there was no t that appears explicitly. The only t was there in the thermal broadening part. Here I have a temperature explicitly. So let me put this t here over here. So that's basically telling you that's the thermal broadening. Not the natural broadening is too small to consider in this case. Thermal broadening is happening, remember, because of the motion of the gas. So this temperature is the temperature, kinetic temperature of the gas. Now let's see. What is this temperature? So where is this coming from? It's coming from that h nu naught by kt. So let's do a remembrance. So this says that in thermal equilibrium, the number density in the upper level by the number density in the lower level is given by multiplicity in the upper level by multiplicity in the lower level, e to the minus h nu naught by kt. It turns out most of the H1 is not in thermal equilibrium. Okay. So what happens, obviously you cannot define a temperature and this equality doesn't hold. So what we do is we define a quantity we call it Ts. It has a dimension of the temperature and this is called spin temperature because this is a spin flip transition. Okay, so this is called a spin temperature because it's a spin flip transition and we have not defined it yet. How do we define? So you say that, well, even if it is not in thermal equilibrium, there will be some atoms, some number density in the upper state, some number density in the lower state. I can just write their ratio in terms of Ts in the following way. This Ts is not the physical temperature. It will be physical temperature only when there is thermal equilibrium. But all the other time I can define Ts by this expression. So this is a definition expression. So you cannot ask the question why. For any definition, one cannot ask the question why. So if that is true, so if it is not in thermal equilibrium, this is essentially the spin temperature that one has to consider in this expression. Okay. So in general, it is true if it is in thermal equilibrium, Ts will become T. Now, this is alpha, right? What about 21 centimeter optical depth? By definition, it is alpha is also a function of S. And then ds. So I just remember the expression because I'm just writing down what is written over here. 3hc square by 32 pi AUL by nu 0. 3hc square by 32 pi AUL by nu 0. And now, see what is happening here is that you have this column of H1 gas and you have, say, we're talking about absorption, so some I nu 0 coming from somewhere. This is the column of the H1 gas. It's getting absorbed here. If I assume Ts is constant over S, so it doesn't change along S, and that is not strictly true. but just for the time being we are assuming, such that I can take this outside and take this outside. Then what I get is, remember this is a big assumption, this is mostly not true, but just for the sake of understanding, I get integral of n ds here, and let me write this as nh1. So these are h1 number density. Where else have I written? Not anywhere else. So here. This is more in general, so it's all right. So h1 number density integral ds. And what is this? This is the column density of h1, right? So 21 centimeter optical depth, if I write is as tau h1, it's 3h c² by 32 pi AUL by nu naught phi nu and then nh1 by ts. So this gives you the optical depth not only depends on the column density, it also depends on the spin temperature. And that's an important information which one can use in the following way. So let's talk about an absorption experiment. The experiment is the following, that say now we are talking about not an external galaxy but an H1 cloud in our own galaxy, and I am an observer here who is looking through the cloud or towards the cloud, say. Now say there is an extragalactic source, some type of source, let's not go into what. It has an intensity I0 and it's constant over all frequency. Okay, so I turn my telescope. So I assume that property of this H1 gas doesn't vary much inside. Inside means inside the gas. So I look at this is a point source. So if I look a little bit away from this source, I can look at, for example, in this direction. So this can be my line of sight. Let's call this line of sight B. Then obviously there is no background radiation. All the radiation is coming from the gas itself. So IB is essentially 3h nu naught by 16 pi AUL phi nu and then NH1. That is the emission, 21 centimeter emission intensity of this cloud. If I look at this direction though, so this I call line of sight line of sight A. And I say that I0 is much greater than IB. So when I'm looking at that, so I don't need to consider IB at all. It's much greater than IB. And so also let's say that tau is less than 1. It may not be much less than 1, but it's considerably low. It's not very large. If it is very large, obviously I will not be able to see I naught. So that's not the case. So in that case, if I consider the line of sight A, what will be my observed intensity IA? It is I naught e to the power minus tau h1. Alright. Now tau h1 is a function of frequency. Remember, all these are function of frequencies. So when I look at this IA, so I can plot it against frequency. Let's see what will I see. So this is frequency, this axis is frequency, and here I am plotting IA. What will I see? Okay, so if I look at frequencies which is away from 21 centimeter, then I don't have any absorption. Then tau is 0, because remember, so let us also write down tau here. All frequency dependent comes from this phi. So this is exactly the expression that I have written here, 3hc square by 32 pi AUL nu naught phi nu nh1 by ts. Exactly same expression. They have just written phi nu away here because this is the thing which gives you the new dependence. The new dependence come from here. So if I look at a frequency which is away from the 21 centimeter absorption frequency or emission frequency, which is away from nu equals to nu naught, 1420 megahertz, then phi nu is 0. Phi nu is 0. IA is essentially I0. So that I can call like a base level. So that is everywhere here. And then what will happen is at the frequency where, when say if this is my nu naught, nu equals to nu naught, suddenly tau nu will increase, and as it increases it takes away radiation from I0. So this spectral line will look something like this in absorption. Okay, so what can I do with this observation? So I have measured this line everywhere. So whatever I have drawn, I have measured this. So I can get I0. So I0, I will just see what is the intensity here. I can get phi nu, because that is the line shape function here, and nh1 by ts, which is from the tip. Remember that at the tip the phi nu has exhausted, so it's the maximum. So there I can figure out what is the thing, which is what is this thing. Or what you can do is you can integrate tau nu over all frequencies. Phi nu will integrate up to 1, and then what will remain is whatever I have put in this curly braces. So I can essentially measure what is the optical depth. Okay, so I have two measurements. I have one measurement which is this, and I have the measurement of the optical depth. So let us write those down here first, and then we will see. So I have measurement of this, which is, okay, and I have measurement of tau. So remember that these lines are in the radio frequencies. So in radio astronomy, we defined something called brightness temperature. This is just attaching a temperature with a specific intensity. So what is the definition of brightness temperature? Well, brightness temperature will be the temperature if of an object of which you are measuring the specific intensity, if that object is a black body. Okay, so if I am measuring the specific intensity of an object which is a black body, then the brightness temperature will give me the temperature of that black body. However, all the objects in that one can measure are not black body. So then you have to give a definition of the brightness temperature, and it comes from the Rayleigh-Jeans limit of the black body spectra. In the Rayleigh-Jeans limit, let me write Rj of black body, I specific intensity is 2 nu naught square kt by c square. So we define the brightness temperature in this following way. We say that I don't care what intensity I have, so it can be the intensity that I measure here. So I multiply it by c square divided by 2 nu naught square and kt. And k. T is, yeah. So this is my definition of brightness temperature. Again, it's a definition of a temperature. You cannot question a definition. Now, what is the brightness temperature for our observation now? So Tb will be, so I have to multiply this by c square by 2 nu naught square k. So if I do that, so I get 3 h, nu naught will go to the denominator, c square will come here. I have 16 pi multiplied by 2 will be 32 pi. I'm missing a k here. I think that is missed earlier also. Will be k, which comes from the kt thing. Yeah. So this k I forgot to write down. Anyway, mistake happens. It's good to have mistakes. So I will get AUL from here by k and nu naught square here, and I had a nu naught, so I get nu naught k and whatever else that I had, which is nh1 and phi nu. So that is TB. You see, now TB is almost, I can divide this by TS and multiply with TS, then this entire thing is nothing but tau. So we agreed that we can measure IB, and if we can measure IB, we will be also measure TB, and we can measure tau. That also we agreed. These two we can measure from the two observations that is happening along two lines of sight A and B here. If I have these two observations, I can put TB here and TS here. I can, tau here. I can figure out what is TS. So I can figure out the spin temperature, which tells me how many atoms are in the upper level compared to the lower level in this way. And when it was measured, it was found that in our galaxy, you get the idea of spin temperature from there. You get the line width, which gives you the kinetic temperature, the actual temperature of the gas. You see that these two temperature doesn't match, which essentially means this line transition has not come with the thermal equilibrium with the gas. The gas can just each one can collide with themselves and can come into thermal equilibrium, give a gas temperature T, which will give you the line width. But it may not have come to the thermal equilibrium with the H1 radiation, 21 centimeter radiation. Then T will not match with TS. And that's what was seen in our galaxy. So it is understood now that most of the H1 in our galaxy are not in thermal equilibrium. Okay, so that's it for today. Today it became a little longer because also today is the last lecture in this unit, which is radiative transfer. So in the radiative transfer, what we have done is we have looked at what we mean by radiative transfer, found the equation for radiative transfer, found solutions of it, then discussed it in detail for a two-level system, and then particularly for this 21 centimeter radiation, which is said is one of the most important radiation and tool in astronomy and cosmology. There are many other radiation mechanisms, and one should study them. And two most familiar ones are the synchrotron and Bremsstrahlung. Unfortunately, we will not be able to discuss those in this course.